Alright, in this video we'll be looking at special patterns of binomial expansion starting with perfect squares. This is nothing that new. Okay, it's really just a convenience, a sort of shortcut for patterns that will be used a lot, and so something you should be familiar with, something you should be fluent with, something you should be able to recognize quite easily. Okay, for fun, we'll draw a picture of what's going on when you multiply two copies of a plus b, so I guess we can visualize a plus b as two different lengths combining together. Then the other copy will be the same two lengths, but we'll make them vertical. Why? Because when we multiply these two together, it'd be looking at the area of a massive square. Okay, now look, I lied. This isn't just for fun. It's actually a very useful strategy in giving a geometric interpretation to multiplication, which actually has some very nice applications going to calculus and so on. Okay. Anyway, let's think through this area one piece at a time. The blue square is just worth a square, so we can put him up there. Then the rectangle there is worth a times b. And before we launch him up, we could notice the bottom rectangle is also worth the same a times b. So actually we have two copies of a times b. Okay. Then finally, the little green square is b square. So we can shoot him up just like that. The way we normally write this pattern is that a plus b all squared is equal to a square plus 2ab plus b square, where often the middle guy is forgotten, just like in real life. It's also convenient to recognize the pattern if there's a negative in the bracket. Notice the negative only applies to the b, so that means that a is immune to the negative. The 2ab must flip to minus, and while b himself is negative, squaring will kill the negative, so it's still plus b square, meaning that only the middle guy flips sign. Okay, so when it's a minus b all square, the only difference is in the middle term. The last pattern is what happens if one of the brackets carries a positive and one of them carries a negative. Okay, so the positive a square is still there. The b square now goes negative because it's a positive times a negative. Then for the middle terms, we have a positive ab as well as a negative ab. So they go away. Okay, and that's all we are left with. That's why we call this a difference of two squares. It's literally just subtracting a square and b square, and that's the pattern to recognize. Okay, this is one of those cases where the picture is really more for fun than anything useful, but we sort of can turn one of the b's negative by looking at negative areas, which I've got in some red shade there. So have a look at what's happening. I won't explain it. You have a look if you're curious, but I'll leave it there. In any case, this box has the three patterns that you should learn to recognize and use. It just makes life a whole lot easier if these come to you immediately and automatically to you in future. Okay, now expanding isn't really where it's most useful because honestly expanding them manually isn't that much slower, but it's when we're factorizing, so going backwards, that learning to recognize this stuff could be quite useful and could be quite convenient. It's a little fake to give examples of this now because obviously they'd be rigged to work, but let me show you what to look out for so hopefully you can easily recognize them when you meet them in the wild. Okay, so here's one. So first see that the first term is a perfect square. Of course, x square is just x square. Then what really gets the alarm bells ringing is the last term, the 36, is also a perfect square. So 36, you should recognize, is 6 square. So you quickly, mentally check if 2 times x times 6 matches the middle term, that's the 2ab from the previous screen. And it does, because 2 6s are 12, and there's the x sitting there too. Great. So that tells us it's a perfect square. So we can shove the x and the 6 into the brackets there. Okay, and finally notice the middle term's actually negative 12x, which means it should be x minus 6 in the brackets, all square. Okay, remember the middle term is the only one that cares about that sign inside the bracket. Okay, next one. 5x squared minus 45. I haven't made a big deal of this yet, but when factorizing, it's pretty important you look out for common factors first. It just makes your life easier as well if you can spot them. So in this case, 5 goes into both of those, so you should definitely take that out first. To get to 5x squared, we just need the x squared. Then to get to negative 45, we need a negative 9. Okay, so look at what we have inside the brackets. We have the x squared again, and 9, we should recognize, is 3 squared. They are subtracting, so it's a difference of 2 squares. Okay, so we make 2 brackets. The x and the 3 pop in just like that. One of them's a plus, the other one's a minus. It doesn't matter which way they go, and we're done. Okay, last one. I reckon this one's also quite easy to spot because firstly, 9 is a perfect square, so we have 3x or square there. Then very suspiciously, 25 is also 5 square. So that's the sort of thing you want to start building your awareness of. Okay, so check the 2ab term. So 2 times 3x times 5. Yes, that is indeed 30x, so we at least try to act surprised. So 3x and 5 will go in the perfect square bracket. And this time the middle term is a positive 30x. So it's a plus inside the bracket as well. So learning to recognize this pattern, again, will make life just a bit easier. Okay, and we'll also be doing a lot of perfect square stuff when dealing with other types of quadratics that we can't factorize. So get to know these patterns well, with the aim that when we use them in full force later, all of this will be automatic to you. Okay, but that's all for this one. Thanks for watching. See you around.